I'm very happy to have today Tanja Lange, primarily from the Technische University in Eindhoven, who will talk to us about S-unit attacks. So the floor is yours.
Yeah, thanks, and very nice seeing everybody. Thanks to whoever was just rotating the camera. Pity for not being there. On the other hand, still feeling very, very safe in Taiwan, avoiding COVID here. So greetings from the warmth in the afternoon. So this talk is about S-unit attacks, but let me start by setting the stage a little bit. So this belongs to the area of lattices. And so lattices are a part of post-quantum cryptography. So cryptography, post-quantum cryptography is cryptography under the assumption, and you have to be careful, the attacker has a quantum computer, the normal user does not have a quantum computer. So this is our current situation. You're sitting there with your cell phones, with your laptops, and what you have in your hands is a, well, classical computer. At least I don't have a quantum computer. But our attacker might be recording our messages from today. They might be having the Zoom session. Well, it should be public anyway, so that's not the concern. But for other things, you might actually care about the long-term effects. And that is bad news for the currently used cryptography, because in 1994, and that's actually a nice reference to ANSI as well, so it was at ANSI 1, Shor showed a quantum algorithm that could break, well, RSA and discrete log-based cryptography. So in quantum polynomial time, well, quantum polynomial time, so it means it needs a big quantum computer. However, well, once a physicist get their success, well, get their act together and get successful, then they can run this algorithm. So it's not like with the normal cryptographic assumptions that, well, maybe somebody could find a better attack. We already have the better attack. What we're waiting for is a physicist to realize the machine that can run it. And to be clear, Shor is not the only algorithm. So there's a big category starting with Grover's algorithm, which only achieve a speed up, which is taking the square root of the exponent. And there are lots of subsequent papers that study quantum algorithms. So just avoiding Shor is not good enough. There's also Cooper work, etc. So if you want to learn more, go to the quantumalgorithmszoo.org to see something. And well, it took a little while, but late 90s, people were talking about how can one avoid this threat of quantum computers, what cryptosystems would remain secure. And so Dan at that point coined the term post-quantum cryptography in a main this discussion, because if you at every moment have to explain the whole story with the attacker and a quantum computer, yada, 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 to just say what you're working on, it gets a little inconvenient. So having a term, well, post-quantum cryptography is useful here. And it took off. So we then had a bunch of workshops on post-quantum crypto, starting with a small one in 2006, something like 40 people. It was fun meeting because like-minded people, but it was rather small. And by now it's grown into something, well, 2018 we had to close the registrations at 380 because that was how many could fit into that venue. And the next edition, in case you're interested in this, is going to be an online edition at the end of September. So registration will be free and you can just participate, and well, talks will also be recorded if you're in the wrong time zone. So NIST after a while was like, well, let's see whether this is interesting to the community. So they held a workshop on, well, post-quantum cryptos, or kind of gauging the interest of the community. And yep, lots of people came. It was after PKC, and some people came just for the post-quantum workshop. And so they had the idea, yep, it's interesting. And so the next year they announced that they would be hosting a competition to figure out what systems should be standardized for post-quantum cryptography. Deadline was next year. And well, you have seen yesterday already in the Psych talk that things have been going on for a while. So the history is 2019 was the second round, 2020 was the third round. So for each round, NIST narrowed the field. Systems that have been broken were kicked out, but they also kicked out some systems where they felt like, well, maybe we have better alternatives. And so they wanted to focus the attention on a few systems. Not sure I always agree with their reports, but at least they give some justifications. And so the third round was down to 15 candidates. And then they said, okay, well, we'll announce the winners end of 2021. And this was kind of a running joke for half a year because NIST kept pushing the deadline. So whenever my students were coming late, I was starting to ask like, hey, are you trying to pull NIST here? And so, well, there was like no later than March, and then March came and March went, and we reached March 130 and still no announcement. Well, finally on July 5th, NIST did announce the first selection. They also said that they are going to continue to investigate further systems. So there are some systems which are moved into a fourth round for further investigation. You heard this yesterday in context of Psych. And they also said that they will even issue a new request for submissions only on signature systems, but it keeps it going. So we're not quite sure whether it's going to end. For the currently selected ones, you feel like, oh, they're finally announced. So are we ready to go? Well, no, it's a machinery. So they say which systems in principle they will use, but they haven't even specified which parameter systems to use. And they say that next year, but probably more likely in 2024, they will actually issue the standards. Before then, there will be one phase where they have a draft standard and invite comments. Now, what's in there? So post-quantum crypto, we have 5 major categories. Well, systems based on codes, hash functions, isogenies, you heard a bunch already, lattices, and multivariate quadratics. And so for each of those, we have a hardness assumption where we don't know good quantum algorithms to break them. However, these are categories of mathematical problems. Turning a math problem into a functioning crypto system is where historically there have been lots of pitfalls. So those who looked in the history of cryptography, you have seen knapsack problems, which are based on a hard problem, subset sum, but they were always kind of missing the hard instance. They always had to stay somewhere in order to make the system functional. And so it can be totally insecure if the problem isn't used correctly. Since I'm often getting a question like, well, so can we actually study this before having a quantum computer? I'd like to pre-answer this question, preemptively answer this question by saying we have a good understanding what quantum computers can do. Kind of, we have an instruction set. We know how a quantum computer should work. What we don't know is the relative cost of these different operations. So really doing the fine-grained optimizations, whether you want to have a Toffoli gate or swap this out for several CNOTs, that we don't have because it will depend on the physical realization, how expensive those are. But we kind of know what we can do. That doesn't mean that we have looked enough. So I'd love to see some more kind of ants people look into these problems because there's a lot of algorithmic number theory problems going on where we would need matching quantum algorithms. All right. So what was the NIST announcement? So on the 5th of July, they announced the winners, namely Kyber, which is a KEM, so a key encapsulation mechanism. Think roughly of something like the Diffie-Hellman scheme, like a way to agree on a key, which you can then use for bulk encryption with symmetric crypto. And that one is used on structured lattices. And then the next one is dilithium, which is a signature scheme, also based on structured lattices. Then there's Falcon, another signature scheme, also based on structured lattices, and then Sphinx Plus. Well, okay, it's not based on structured lattices. It's based on hash functions. So there's a little bit of a variety of assumptions, but 3 out of 4 are based on structured lattices. My reading of this was it was a pretty odd choice because, I mean, I was motivating the concern that we have with building post-quantum systems as, well, we have to make sure that our encryption gets moved to something that quantum computers cannot break the day before tomorrow. I mean, like today, right? I mean, like, do not wait. However, there's only one of those which is good for encryption, and there are 3 which are for signatures. It's a bit of a choice, of course. I mean, I'm on the Sphinx design team. I'm happy to see Sphinx there. I fully endorse Sphinx. I think it's a good design, and I'm happy that it's there. But why only 1 KEM and 3 signature schemes? It's beyond me, but well, NIST made this choice. They have now some runner-ups, so to say. So they have 4 schemes in round 4. That means they're considered for future standardization, but want a little bit more attention on them. And well, the last one, Psych, maybe got a little bit too much attention lately. So what is left then are 3 schemes, which are KEMs, and they're all based on codes with or without more structure. Okay, So what is lattice-based cryptography? Now, one thing that always cracks me up when I talk with theoretical computer scientists is that they tell me, kind of in their introduction to what is post-quantum cryptography, they tell me, oh yeah, quantum computers break number theoretic cryptography. Well, I mean, we're here at ANS, so we're doing the number theoretic cryptography in the crypto part. And to me, lattice-based cryptography is, well, at the core, it's a number theory algorithm. So ANS3 is the publication for the Entro system, which, well, when I was a young student in 2000, Jeff, I think it was Joe Silverman giving the talk, but could have been Jeff Hofstein. They were saying, okay, well, there are different ways to expand this acronym, but one for Entro was number theorists are useful. So to me, Entro is totally number theory system, but other people will put it into a, well, theory of computer science. Anyway, we're talking about lattice-based cryptography. And we're going to talk about structured lattices. So the Entro system is working in the ring of polynomials over the integers, modulo a cyclotomic polynomial. So modulo the polynomial x to the m minus 1. And their choice of m was a prime. And then they also, in addition, work modulo q, which is some large power of 2 in their systems, and in other places they work mod 3. It's something which makes it a little bit cringe when you're a mathematician, because, well, q and 3 are co-prime, but they have it in a way that is uniquely defined with some lifting to the integers and going back, etc. Some years later, in 2010, Lubashevsky, Peikert, and Regev, well, I put introduce in quotes because it's very, very close to the Entro system, but they introduced what is called the ringed LWE system. So that's learning with errors based on rings. And the rings that they're using are very, very close to these Entro rings. And then for the system, they have a proof, and that's where the theoretical computer science part comes in, where they relate the hardness of different steps to one another. At the bottom, that's the secure, well, that's a practical crypto system that they want to use. And at the top is an assumption where they assume it's hard, well, at least they say it's hard for a polynomial time quantum algorithm. And what is supposed to be hard is a worst case problem in ideal lattices. And so that's what our talk will focus on, looking into these ideal lattices and then looking at, well, how we can solve these problems. There's another ingredient which is saying that, well, the assumption is that the ring LWE system is pseudorandom. Is there a question? No, okay. The ring LWE system is pseudorandom, and with these combinations, so you have like a worst case and average case, and so you're then getting the security of this crypto system from it. Now, when you look at the concrete choices, then they assume something, well, not just polynomial time quantum algorithms, but, well, it should be hard for an exponential time quantum algorithm. So like the parameters for Kyber and dilithium do not quite fit this reduction, but that's unfortunately a typical thing we see in crypto systems. There is a proof for something. You use this as a kind of basis for your comfort feeling, but then you go choosing the parameters for something which is, well, unbreakable with some security margin. So the typical structure of these ideal problems, so the worst case problem on ideal lattices. So what do they look like? So in Entro, I was already mentioning, we're looking at this ring. So we're having a prime m. So, well, okay, to make this a cyclotomic, you would divide out by x minus 1. But what all these three modern schemes are using, so the three winners which are using structured lattices, is actually power of 2 cyclotomics. So then you have, well, x to the m minus 1, and you have one factor which is irreducible, namely the x to the m over 2 plus 1. And since I don't want to write everywhere m over 2, I'm just calling that thing n. So the relationship between the m and the n, so we're looking at 2nth root of unity. And so for the remainder of this talk, I'll only look at power of 2 cyclotomics. So my n is going to be in the set of 2, 4, etc. So I'm sort of excluding the rationals here, and I want at least to have the complex numbers. Well, I mean, sorry, the Gaussian integers for the ring here. Okay, so the ideal SVP, which is the thing which quantum computers should have a hard time breaking, at least in polytime, is you're giving a non-zero ideal in this ring, and you're supposed to find a short non-zero element there. you guarantee that there exists such a short element. So this is by the setup of how this ring and the ideal were constructed, like how the crypto system works. There is a short non-zero element, and then you can break it if you can find such a short non-zero element. And typically there is a little bit of slack. You don't have to find exactly the G that somebody has put in. You can find, say, rotations of G, sometimes even small multiples of G are okay. And there's some, well, this is the ideal SVP, so you want to find a shortest. But what we normally look at is the approximate ideal SVP, so you're finding something which is within a multiplicative factor of the shortest length. Now I have to give you this ideal, nice math abstract object, but I mean, I have to give you a concrete instantiation. So the ideal is given to you as a basis over this ring. So you have this cyclotomic ring there, and the ideal is given as a linear combination of all these basis vectors. No, okay, so what you're going to do is you're going to take, well, combinations of this. Let's take a small example. So n is 4. We're looking at the eighth rules of unity. And so here is one ideal. So I'm giving you these 4 equations. And then with some magic, which, well, I'll hope to explain to you in this talk. Now, the first magic is not too much because I'm just doing a baby system, just dimension 4. You're looking for combinations of those, and then you're finding the combinations of taking 2 times the first vector, 3 times the second, minus 5 times the third, and minus 2 times the fourth. And you're getting something which, yep, indeed looks a lot shorter. So if you look here on the left, it is a kind of diagonal system. So you're having only coefficient 1 in front of the powers of x, except for the constant term where you have big numbers. And this one is a lot more balanced, and everything is much, much smaller. So we're going to look at shortness in the Euclidean norm, the L2 norm. And so, well, this looks short. How do we get there? Let's write this into a matrix. So each row is now one of these systems. So this is the V4, this is the constant, this is the x plus this one, x squared plus this one, x cubed plus this one. So this is our system. And then I want to reduce this. Well, I have to take integer combinations. So I can't just like do Gaussian elimination, but I can take, well, let's take this first one and see how often we can subtract it. The other 2 are smaller, but we can subtract it once from the last one. And then we moved on to the next one, the 540, and see where we can remove this. It fits in the first one, doesn't fit anywhere else. Then the 247, we look where we can put this. It reduces there, it reduces there, doesn't reduce the last one. And then finally with the last one with 192, we reduce those 2. And then we start over. So then we reduce the last one with the previous one, as far as we can go, and lots of stuff is happening. And then we trickle up again. So this is basically what LL would be doing. So we are always looking at pairs of equations, trying to find the closest which we can reduce. And eventually, well, this trickles up and trickles down. So then we finally get this example that I had on my slide. Now, this doesn't look too bad, but this doesn't work when n is large. So if you have a large dimensional lattice, this is not computable in efficient time. So this would be, well, it's computable efficiently, sorry, I should be precise here. You have a polynomial time algorithm called LRL, which does basically this here, but it doesn't get it really short. So there's an approximation which has an exponential factor in there. You want something, well, can take an approximate SVP, but it has to be reasonable. And LL is too far away. So let me first go into what we can expect. So I want to have lower bounds and upper bounds on how short such a vector could be. So I'm starting with the ring, so with my cyclotomic ring here, and then with an ideal, and I want to figure out how short I can expect a vector to be given by lower and upper bounds. Okay, and I should also fix the embedding. So far, I've been using the coefficient vectors. Actually, for some of the theoretical results, we need the Minkowski embedding. So what we're doing there is we take embedding of the number field. So here we have the 2nth cyclotomic field, okay? And then we're taking these iota 1 till n-1, and then, well, the inverses of those to be the embeddings into the complex numbers. So these are the complex conjugate pairs, and I lined them up so that they well, the -1 is to be interpreted as 2n minus 1. Okay, so then the length is a normal, well, the absolute value is a normal absolute value in complex numbers. So it's the integer, well, it's a complex number times its conjugate, and then square root of that. And so if you look now at the what happens to elements, if I use this embedding, so we're taking elements of the ideal and applying this embedding to it. So what we see here in the example, well, the 1009, well, all the embeddings are the same, so I'm just getting to 4 times the same number. With this one, well, I'm mapping x to the 8th root of unity. So this maps to 8th root of unity plus 1247. So this is just moving over, replacing x by zeta 8. And then I'm having the, well, conjugates. So I'm replacing zeta 8 by zeta 8 to the cubed, zeta 8 to the -3, and zeta 8 to the -1. And then the same for the other basis vectors. And okay, not very interesting what's happening here, but now I have a basis, a 4-dimensional basis for my lattice. And you can use the norm of the ideal and the discriminant of the field to estimate how large it is. In particular, getting a lattice where the co-volume is, well, the discriminant, so the square root of the n to the n times the norm of the ideal. And in this particular case, well, the dimension is 4, so we're getting 4 to the 2 times the 1009, and we will be seeing that this grows something like with the dimension, so I want to have a 4th root taken out of it, so I'm getting this 11.27. Okay, and now to get a lower bound on the length, remember that I'm looking at a g which is in this ideal, so the norm of the element is no smaller than the norm of the ideal. So if I look at the norm, well, okay, that's the product over these embeddings. That's why the Minkowski embedding is nice here, because it gets the nice, or gets a correct number theoretic structure. So this is the norm of the element, and it's lower bounded by the norm of the ideal. And then, well, I actually need the L2 norm. So I need to relate these absolute values to what I have a nice bound on. And okay, that's just the usual estimates where you're taking like the nth root and getting a square root of n outside. And so then I have something which is related. So this is inside here is the norm of the ideal, sorry, of the element, which I know is lower bounded by the norm of the ideal. And up here, well, this was the co-volume. So what I'm seeing here is exactly the nth root of the co-volume. Okay, so going through this example, how short could I have expected to find something? Well, I found this vector which has coefficients 2, 3, -5, and 1. So if I look at the coefficient norm, then it would be just this part down here. But if I look at the Minkowski embedding, what I'm seeing extra is a square root of 4. Well, you can trace through this. So this is the full Minkowski embedding. If you look at what the norms, or what the absolute values are, each of those gives me the same integer part here. And then the other parts nicely cancel. And so I'm getting 4, 1, 2, 3, 4 times the same value. So that's where the square root of 4 comes from. And then times this absolute value. So the norm of the coefficients is linked to the norm of the Minkowski embedding. And what we found is, well, yes, 12.49, which is correctly upper bound and lower bounded by 11.27. So it's not a contradiction. We found a short vector, but it could have been even shorter. But it's pretty good. Now an upper bound is given by the geometry of numbers. So that's another relationship which again involves the co-volume. So that's again our norm here and times a discriminant. And then a factor of n/2 factorial to the 1 over n. Okay, so the main thing there is a n factorial to the power 1 over n. And so this thing still grows. So if you're looking at how this behaves, that's, well, down here, this grows like the square root of n with some coefficient. So it makes sense to look at what this upper bound is in terms of, well, what we can hope for divided by the constant which comes in from this ideal. So looking at this part, so this is where the ideal matters, and here only the dimension matters. And so, well, this would be the Hermite constant, but I'm going to use this eta also for talking about the quality of a lattice. So I'm just saying it's the Hermite factor for a concrete G. I'm computing the ratio of the L2 norm of the Minkowski embedding divided by the nth root of the co-volume. And so that's the Hermite factor for this particular G. And okay, can do some computation. So we know we have a lower bound, we have an upper bound, and somewhere in between there, we have a vector. It exists. The question is how we can find them. Now, the normal approach to finding short vectors in a lattice is to run a whole bunch of algorithms which use the additive structure. So nothing specific to our ideal, nothing specific to these number theoretic rings. We just have some lattice, and then we're doing operations. So LL is similar to this baby example which I showed you. Then there's the family of BKZ algorithms, where BKZ beta means, well, instead of having just two lines or a box of two that we're looking and optimizing, finding the shortest, reducing one with the other, we're now looking at a box of beta such vectors with appropriate projections, etc. And then we need to find the shortest vector from this box of beta. So beta has to be such that it's reasonably computable. For instance, 80 is a dimension where you can do this efficiently. You can actually find the shortest vector repeatedly. And so then instead of having the LL, where you're just reducing one vector with the other, you're having a box of beta such vectors, and you're reducing those with each other. And then you go into the next box and you go to the next box, etc., etc. And you're doing multiple tours of this. So what you can hope to get, now I'm not taking the Hermite factor n eta, but I'm taking the nth root of it. So that's the root Hermite factor. And that one, well, converges to n, to 1. Remember, this was something like growing with the square root of n. So if you're looking at the square root of n, and then the nth root of that, that converges to 1. And okay, these are getting better and better. You can hope to find a vector within this. If you're using BKZ 300, you can hope to find a vector within this if you're using LIL. That's what these numbers mean. So these work for arbitrary lattices, but we actually have these special lattices up here. So for a normal lattice, you would just have the determinant of the lattice up here. So can we do better using the ideal structure? And that's the main focus of this talk. Now, I've already been talking about these embeddings, but I want to formalize this a little bit. So let me do the notation. And in particular, I want to have the vocabulary of infinite and finite places available. So again, I'm using the mth root of unity here. So m is 2 times n. And then I will only look at odd powers of it. So if I'm looking at odd powers of those, then I'm getting, well, taking that to the nth, I'm getting -1. So I have a unique morphism between k and the complex numbers. So these are my embedding. And like before, I'm rearranging them in this nice way. And so I have my embeddings here. Now the notation I want to introduce is calling these the infinite places. And I'm deviating from what I was using before. So before I was using the absolute value from the complex numbers. And now I'm merging two of them together. So instead of taking the square root, I'm taking just the product of the embedding of G and the complex conjugate embedding of G. And that means, well, I'm having kind of two copies of the same. So I'm having the places with the positive numbers here, or I'm having the places with the negative numbers, and they give me the same information. So I will restrict to taking just one of those. So instead of having the n here, I'm having n over 2 for those because it's only half of them. So there's still the relationship between the coefficient embedding and the Minkowski embedding if I run through the same computations there. So notation, if I'm writing sub c on this absolute value, that means the square of the embedding, well, iota sub c, and then, well, this the complex conjugate with it. Okay, so then finite places. Now it gets interesting. So we know finite places or finite valuations from, say, integers. And so we're looking at the valuation at a prime. Now we're in a more complicated ring, so we're looking at prime ideals there. And then we're defining the evaluation at a prime ideal of this ring by this expression. Now, this first part, this the size of R mod P is the norm of this prime ideal. And then to get this valuation, I'm taking this to the power minus the order of my element at this prime. So I'm looking how often can I divide G by P, and then negative of that is the exponent there. And so these maps, where I'm mapping G to this G evaluated at P, those are the finite places of my number field K. So this is standard, like if you work in these fields, this is how you always define them. There's some changes sometimes, whether you taking this number or take some other scaling factors, but this one is nice because it gives you the product formula, so you can take the product over all embeddings, and then you're getting 1. Now, what can we actually expect to see? So when we're looking at, well, what prime ideals would happen, I don't need to try every prime ideal. So if I'm having the mth cyclotomic field, remember m is 2n, so I'm looking at this polynomial x to the n plus 1, and I'm trying to figure out what prime ideals I can actually find in this R. So then there's one which is like the prime 2, because, well, I'm in the power of 2 cyclotomic fields, so I will always have that x plus 1, and so if I take this x to the n plus 1 and I reduce it mod p equals 2, then I'm just having x to the n, then I always find that this is, an n is a power of 2, I'll always find this is a pure power of x plus 1. So there's a prime ideal over 2 given by 2 times this ring plus x plus 1 times the ring. And then the other primes I can hope, well, let me just go through the degree 1 primes. So those are the primes p which divide 1 plus 2n times z. And so my example before, I had n is 8, so 2n would be 16. So I would be looking at primes in the arithmetic progression 1 plus 16z. For instance, 17 would be in there. So I can expect to find a prime over 17, but I won't find a prime over 13 or 7, etc. And for those numbers, for these primes, I have a complete factorization. And, well, okay, if you have larger degree primes, then you're having higher order factors there. So then it's not p in there, but a power of p. And then the prime ideals are given by, well, p times r plus these individual factors. So let's do an example. Here's an example for 8 again. I already announced that I want to do 17. So these are the 4 factors that we found with 17. And so these are the 4 prime ideals over 17. And so the valuations, okay, the norm of this prime is 7. So this prime ideal is 17. And then for each element G, I have to compute the order of G at this particular prime ideal. So those go here in the exponent. These are just the infinite places. And remember that I'm merging them two together. So I'm only having the infinite place that you see here. So it's only the one at 1 and at 3, because the -1 and -3 are just the same there. And then, well, what's the next prime of this arithmetic progression? So conveniently enough, 17 plus 16 is 41. 41 is also prime. So I could just trickle through finding all my primes there. And so I'm getting my valuations there. Now, that allows me now to define one word of the title, namely the S units of this field. I will always include all the infinite places in my S. So that's not uniform through the literature. Some people just look at S as the finite places. I find it easy to go for S including the infinite places. So pick one, stick with this. So for this one, the infinite places are always included. I don't want to consider valuations at something which doesn't include all the infinite places. So how do you pick this S? One is you can just say, well, you only want the infinite places. That is the very basic attack we're going to look at. Then you can have, well, infinite places and then just 2. We've seen that the prime 2 is always available, or the prime above 2. Or you can say you're taking all primes smaller than, well, some bound y for some well-chosen y. And then the definition of an S unit is that if you take an element, well, your element from the number field K is an S unit if the ideal generated by G factors only into prime powers of the ideals, well, of the prime ideals in S. So looking at an example, just taking like the integers, yes, I had excluded n equals 1. I don't normally want to have k equals q there, but it's easy to argue about this. So if you're then taking the S units of the rational numbers, where I'm picking infinity, 2, and 3, so then I'm allowing myself numbers, integers of the form which are powers of 2, and I'm allowing negative exponents there, and powers of 3. So it's something, it's integers, well, it's fractional ideals where the largest prime that appears is 3. So 2 can appear with arbitrary powers, 3 can appear with arbitrary powers, but nothing outside. And then, well, I said this has something to do with lattices, and there's actually another lattice coming up. So this is not our original lattice, this is the S-unit lattice. So what we're going to do now is we're going to take the lattice that you get from the valuations, and we take the log of that. Okay, so first of all, when you're outside your set S, that means the valuations are all 1. So we can just ignore those. I mean, the definition of an S unit is that the valuations outside S are all 1. There are no numerators or denominators, divisible primes outside our S. And then we're looking at the vector which we get from all the valuations at V, and here I'm again including the infinite primes as well, infinite places as well. But outside S, well, the value is 1, so the log of that is 0. And so I'll look at finite length vectors, which are just taking these embeddings. And then in my example down here with Q, then I have that I'm looking at the number here. Well, if I look at a number of this form, then the absolute value is a power of 2. Log of that is the power, well, that goes into the Z here, times the log of 2. And then the evaluation at 2, well, the prime ideal at 2 has cardinality 2, or norm 2. And so we're getting minus 2, the log of that to the Z. And the same with split. So this would be the lattice there, and the general S unit lattice is the one up here. Okay, so getting towards the full title, so I want to introduce S unit attacks, but I'm first doing a special case, namely unit attacks. So I'm just going to take the infinite places, so just S being infinity, just the normal embeddings. And so that means that the S units in this case are just the units of R. Okay, so all invertible elements of R. And then the algorithm is taking a non-zero ideal of R. Yeah, that's what we have to solve. And we have to find a short generator or short element of. And then the basic case is assuming that it's a principal ideal. So we're trying to find a generator of I. And what we're starting first, we want to find a short one, but we're starting with just some generator. So give me some G which generates I. And then for this step here, there are some quantum algorithms, there's some classical algorithms to do this. I have references on the next slide for that. And then what the S unit attack is doing, we're taking this G, we're computing the embedding into the log unit lattice, and we're trying to find a unit close to G. You can just think of this as a number theory computation. You're finding a unit and you're dividing by it or multiplying it by it, depending on which way around you're thinking. But to make this into a lattice problem, you're looking at the log units, and you're looking at the log unit lattice, and you're looking at the Minkowski embedding of this G with all the infinite places here. And then later on, it's going to be the finite places. So history, this is going back till at least 2014, when Bernstein put a blog post up saying, this is something we're using in number theory, and this should be a threat to lattice-based cryptography. And then the same year later, in October, Campbell, Groves, and Shepard showed that you can come up with, well, they used a quantum algorithm to find this short generator, this initial generator, and then they showed how to use the unit lattice to come up with a short version there. And then this attack was analyzed more by Kramer, Ducal, Packard, and Lange. So Kamelgraf Shepard, the paper is actually explaining it on a system that they made of themselves. So that's a soliloquy system. So when you find this paper, it's soliloquy, a cautionary tale. But it turns out that that system is the same as 2009 Gentry when you instantiate it with cyclotomics. And there's also a paper by Smart and Vercauteren, which is using the same system. Now, S-unit attacks have a different step 0. So in the step 0, we're using also a finite set of places in addition to the infinite places. They're always there. But then afterwards, well, same input, we're getting a non-zero ideal. We're finding now not a generator, but an S generator. So this already gives you a little bit more flexibility. That means it doesn't have to be a principal ideal. And so you're coming up with some G, so that G times R is, well, I up to powers of the primes in your set. So this is a relaxation. We don't need to find a generator. We're finding an S generator. And then we find, well, S units which are close to G over I. So then we can reduce modulos, and we're eventually finding a shorter G with the same property. Step 2. So I already said that we have this in the normal unit attacks, but we also have this in the S-unit attacks. So there's a polynomial time quantum algorithm from Bias and Song. Actually, they wrote the paper based on Eisenträger, Holger, and Kitaya Song, where Kamelgraf and Shepard somehow assumed that this was already the whole thing, but they showed, no, you actually need some more to make this work. But then, okay, fine, it works. And if you don't have a quantum computer, you can use 2014 Bias and Fiekers to run in sub-exponential time to get such a S generator. Now, step 3 here, where you're finding S units that are close to G over I. Well, this will be some iterations. We're trying to reduce something. So here we have this S unit lattice, and we're trying to solve a closest vector problem. So we have our target G, and then we're trying to get close to it by other vectors. And so we first need to have a good S unit lattice. And so there it matters how short these vectors are that we find in the S unit lattice. And so again, the history starts with some blog posts and some mailing list statements saying, okay, well, this is scary. We should actually watch out for that. And then Kramer, Ducal, Veselowski are already using this. This is kind of more in the history of the unit attacks, because it shows how we can extend those to non-principal ideals. So you're finding close principal multiples of the ideal. And then the first full analysis of S-unit attacks is by Pellet-Méry, Henrot, and Stellé. And then there's further work, well, and ours. Okay, so this is kind of the blueprint of an S-unit attack. Now, that gives you lots of questions, but let's start with the unit attack to just come up with how we find those units. So cyclotomic units. Well, first of all the powers of x and plus minus of those are units. To see this, well, we're computing modulo x to the n plus 1. So if you're having x to the n minus 1, that's the same as 1 over x. So this is actually a polynomial. So this is the one to show that x is a unit, and you can have matching pairs everywhere. A little bit less obvious are the following. So if you're taking 1 minus x cubed over 1 minus x, well, okay, that is an element of the ring of integers. That's correct. You see it's just positive exponents there. But why is this the unit? Why is the reciprocal also an element of R? Now for that, I will expand my x to some appropriate, well, by multiplying by some appropriate power of x to the n. And now for my number 8, I want to have it divisible by 3. So for 8, I could just multiply by x to the n, which is the same as 1. And so I would have x to the 9 there, which is divisible by 8. But if it was a different power, if I would use 4, or if I would be using, oh, sorry, and n is 4, so I actually need 2 times 4 to make this work. I was already with half of the solution. So what I will need is 2 times n squared plus 1. But 2 times n squared, well, is a multiple of n. So what I'm looking at the first part here is just 1. And then there's the plus 1, which comes from the x. So this is again some number and then, well, some integer. And this is a multiple of 3, so I have an exact division here. Then I can extend this not just to 3, but to any odd power. So I'm taking this unit, which I have just found, and moving it to 1 plus x to the c plus x to the 2c. So that's also a unit. And well, I can multiply by these up here. So I can symmetrize these by dividing by x to the c. And then I get this. So I have a nice symmetry around 1. Okay, so this gets me a whole bunch of units. And then depending on the cyclotomic field you're in, this might already be the whole thing. So powers of x and powers of these units we've just seen has a finite index. And this is the h plus. And for power of 2 cyclotomics, well, you can prove under GRH that this is h plus equals 1. Well, for now, it's up to 256, including the 2014 Miller paper. And also the heuristics say true, this should stay true for all powers of 2. So we will assume that the h plus class number is 1. And that means that I have a principal ideals in the real subfield. Okay, so going back to our example here, so the unit lattice are these 4 complex embeddings. And then the log unit lattice of that, I'm taking the logs in all these coefficients. I'm not looking at S units at this point, just at units here. And then I'm looking at these 4 embeddings indicated by the odd numbers here. And so then if I look at what happens to the units that I just found, so this U1 is that one up here. So that's the first one we found, the 1 plus x squared divided by x, the whole thing. And then the other ones you see, these are just rotations of the first ones. Now, when you look at those, you see that there's a relation. And so actually they don't give you a full dimensional hyperplane, a different dimensional plane. So you have n over 2 of those. And actually it's still 1 dimension too much because there is this relation that the sum of those 4 sums up to 0. So we have a 3-dimensional sublattice in the 4-dimensional space here. And so lattice spaces for the S unit lattice is given by those 3 first values, so U1, U2, and U3, or their logs. And these are pretty short. So we actually, for the power of 2 cyclotomics, have a nice short basis of the unit lattice. Okay, so then how do we reduce? Let's assume for now that the ideal is principal. So we get our generator by invoking quantum magic, or by using, yes, Fika with a sub-exponential time algorithm. Then for this thing, we compute the log unit embedding. So we're getting this value here, this vector. And then we take G and replace it by G times U. Now, what does it do on the vectors? If I'm looking at these vectors, then multiplication in the logs means addition. So I'm actually adding the log vector of U. So I'm running through my units and I'm trying to figure out which one gives me something shorter. And it's easy to track how short we got by just, again, relating the coefficient embedding to the Minkowski embedding. So I'm looking at the coefficients that I have, and if those are small, then also the Minkowski embedding is small. So what I'm doing there is I'm taking this log embedding of G and I'm adjusting modulo this unit lattice. So I will not just take the basis vectors, but I typically have a pre-computed combination of these basis vectors, which are pretty small. So I want to have small ones there so that I have a good chance of getting close, but I don't just want to have the basis vectors because else it would take too many steps. Okay, so I'm trying this a whole bunch of times. I'm repeating this and I might re-randomize my G up there. And so that at the end, I'm keeping the smallest that comes out of it. And so to be clear, I know that this hyperplane is orthogonal to the norm. This was already on the last slide, that the sum of those vectors is 1. And so the norm, well, if you look at this with logs, then you're having, well, exponential of the logs. And so the product of those is 1 because we are looking at units here. So what we're reducing by is just changing something with orthogonal to this norm. Experiments for this case, so we're looking now at small prime powers at 2 powers, so n equals 4, 8, and 16. So what's in this table? So this is taking, again, this root Hermite factor, so the nth root of eta. So eta taken as the shortest you actually find in experiments. And then in the model, well, let me start with the actually shortest. So this is taking the lattice that we have here and then running BKZ on it in order to find something. So we're finding a short vector in this lattice, and then we're computing this root Hermite factor. Well, first the Hermite factor as the ratio of that by the nth root of the co-volume. And then we're outputting this eta. And so this is what you can achieve. And then the attack, that is doing the unit attack. So that is taking the approach which I had on the slide a few steps back. So I'm finding a generator, I'm reducing modulo the unit lattice, and I'm getting some G out of that. And then I output, well, the length of this vector. And you see up here, this attack is finding the shortest, and then it gets slightly worse. There's a difference in the last two digits on the slide and also here. Now, what are the other columns? The model and the tweak. So in the model, I'm not starting with the sort of expensive computation where I would have to find a generator. I'm just starting with a random hyperplane point. So with something based on down here, well, I know that the unit hyperplane is where to find this G, so I can find my G in the right hyperplane. I'm picking a random point there and then reducing that. So I'm not starting from an actual I, I'm trying to figure out what is the shortest from this hyperplane span there. And so here I'm getting numbers which are somewhat smaller than this. That's the model. And then the tweak is already looking ahead a little bit to the S units. So this is not just taking the unit attack, which is the attack column here. And you see it's getting somewhat shorter, and it's getting, well, exactly the same for n equals 8 and just one difference in the last digit for the n equals 16. The tweak is already taking our first S unit, namely the 1/2 of the final places in there. And so what I'm doing is I'm updating my I or my G by powers of the prime above 2. And what we observe is that this gives us often something which is closer to the S unit to the unit lattice, or in this case S unit lattice. And so the attack is a bit more powerful in finding a short vector. Now, all of these, I mean, these are baby examples, but if you're even within something larger than this, you will be breaking the crypto systems because the approx factor in those is much, much larger than what I'm looking here. Okay, I realized that I'm a little shorter on time than I had hoped for. So this one is kind of a summary slide, what I can do for cyclotomic powers of 2 in particular. So I can come up with some nice S units. And so if I'm looking now, not just at the power of 2, well, the primes above 2, which I had on the previous slide as a tweak, but also at primes, these degree 1 primes here, then I'm getting nice S units from the Gauss sums. And so these gives me reasonably short, but particularly nice to write down S units for these primes given here. And Dan Bernstein gave a talk last year at the SIME AG, so that's the applied algebraic geometry SIME chapter, where he goes through a lot more details on these S units, so how to find these and how to do computations with them. And if you look at previous papers, for instance, there is in Lucas, Plançon, Veselovsky, they use Stickelberger and augmented Stickelberger lattices. These are actually, well, theoretically justified and nicely explainable as exponent vectors from these factorizations of these Gauss sums. So the Gauss sums is getting a larger S unit lattice and a nicer S unit lattice than they have. But it's, I mean, it's in the same family, but it's it makes me happy as a nice math description to actually know where they come from, and it goes through Jacobi sums. So back in the days when I was a master's student, I did my thesis on character sums, so yay. All right, so when we looking at how we would, if you don't have a nice structure, how would you find S units? Or how do you get S units in your normal class group computation? It's often called sieving. On the other hand, it's kind of confusing with too many sieves running around. So we're trying to coin the term filtering for it. And that's just saying, well, we're starting with small elements because small elements have small norms, and small norms are more likely to factor into primes upper bound by something. And so then you hope, well, you factor those and you hope that the only primes you see are primes where you have elements above those in your set of S units. Now that leads a lot of computations of norms and factorizations, and Dan Bernstein's talk tomorrow at the end of ANS is speeding up that step. And so if you have only small primes, you could basically do a trial division. At least you don't need a quantum computer for this factorization. And you definitely benefit from backed factorization. You benefit from knowing where to look. Okay, so then you look at the normal heuristics that we use for, say, number field safe or class group computations, and you see what we normally use as these bound, namely we're using y squared plus little o of 1. And then with this, we're seeing how many S units we get, and we know how many choices we have. So I'm not going through all these steps, but the normal estimates, these are the normal L of 1/2 estimates. Now, these computations are very close to what we're doing in the number field sieve. And there we have the possibility of going to extensions to reach an L of 1/3. So it's actually attractive to think about, can we do these same tricks also for these class group computations? I'm not aware of anybody having done it. And we were only using the L of 1/2 here, but maybe you can even get an L of 1/3 here. Another nice thing, if you want to find all your S units, well, you can use automorphisms. So if you have one S unit, you're using the automorphism of your field to find, well, typically n independent S units. Now you might go like, hey, I might have an S unit from the quadratic subfield. Say I'm having only invariance under n/2, and well, that's actually a great situation, because that means if you're coming from a smaller field, that means your unit has a smaller norm, and therefore it makes it smaller, makes it more likely to factor into small primes. And so we actually like these subrings for amplifying our success chance, and we also like these subrings in order to speed up the computation. Again, tomorrow in Bernstein's talk, he's going to talk about how this speeds up the norm computations. And there are some cases which are not the topic of this talk, not our two cyclotomics, where just using all these subfields is good enough to find the complete S-unit lattice, unit lattice as well. And for instance, multivariate quadratics, or there was a nice paper at ANS in 2018 by Bias van Vredendaal. And so, yes, this is something that our community is good at, and which is, well, I'm giving the talk here. So just to give an overview of what we're doing. So in order to find our S units, we have our units, we have automorphisms, we have this prime over 2, and then, for instance, with filtering, you're finding random units or random S units. We might go for the real subfield and then looking at those guys, or we might use these special S units coming from Gauss sums and Jacobi sums. Now this slide I really want to go through, and I know you're getting nervous over there, but bear with me, please. So this is a simple variant. There's many speedups that we're skipping. So if we're taking log of y to be n, which is the dimension, to the 1/2 plus little o of 1, and then defining this set of S units, or defining S to be the infinite places and all the primes of norm less than y. Okay, then we pre-compute the S units, which are smaller than this thing. So this is the normal step that you would also do with the class group computations. And then the steps in the S unit attacks, you're finding your I, well, you have your I, you're finding a generator, and you're randomizing by multiplying by primes in S. Well, so if you have an S unit, you're multiplying by primes in S, you keep your S unit. You're finding your S generator of I, so you can actually pull this through. You only have to do this step once, and you can do it quantumly or classically. And then you want to have something which actually generates. So you have to get rid of the denominators, but in the power of two cyclotomics, we can assume that the H plus is 1. And so we have generators of these primes from the real subfield. And so we can just multiply by those generators of those, which increases the numerator. So we have a bit more to do in order to shorten it, but we don't have to worry about divisions anymore. I mean, about getting negative anymore. And so then we are replacing G by taking some ratios of units, or in the log unit lattice or S unit lattice, speech, we're taking plus u minus v, and so we're getting closer and closer to a short element. We're repeating this a bunch of times with these vectors until we have a short element. And then the normal heuristics tell us that this will reach a Hermite factor, which is upper bounded by the square root of n, which is, well, what the Minkowski bound gives you in time, which is sub-exponential in n. So we're having the n to the 1/2 here. And so we're getting a shortest vector, or within epsilon of a shortest vector in sub-exponential time. Now, with cryptographic assumptions, we normally don't actually need to go that far. But this approach, when you follow through all the steps, would get you this far. I have 2 more bonus slides, which will be online to justify this. But at this point, I think I should stop, and thank you for your attention.
So thanks very much for the wonderful talk. We are somewhat over time, but I guess we have a time for the quick question, if there are any. Yes, please.
I have a question. I actually just also asked this on the Zoom. You mentioned at one point the case where n is not a power of 2, just very briefly. I'm actually interested in this for another reason, nothing to do with cryptography. If n is a product of lots of small primes, are there good algorithms for finding these short vectors or ideal generators which are better than just this general case?
Okay. Audio quality wasn't great. So what I understood you asking is that you're asking for something which is not a cyclotomic, not a power of 2 cyclotomic, but a cyclotomic where n is the product of numbers?
Lots of small primes, yes.
Lots of small primes. Yeah, so the best analyzed cases are the ones which appear in cryptography, so powers of 2 and single p, but I don't see any obstructions. I mean, some of the nice speedups, like with these Gauss sums or with the multiply by this here, then you can't do those. So you have to work a little bit harder on reducing here and making sure that you don't have, that you're actually in the ideal and not just in the fractional ideal. But that should follow through and give you a sub-exponential algorithm. I think you were asking something that you could hope to get it faster or not, but there I didn't get the question enough, and might be easier to read. But I don't have Zulip on this tablet.
Okay, sure, that's all right.
Thank you. If one very quick question, another one, we could take that one. Or, okay, if not, then let's thank the speaker again. And